Hey dudes, Dude the Builder here, and in this episode of Zig Master, we're going to be taking a look at allocators in Zig. Basically an introduction on the use case for allocators and how to use them. So we are going to start out here with some aliases for convenience. We're going to need heap, stud heap, and we're going to be printing out stuff. So let's use stud debug print. And here in main, I have these lines stored away. These three lines are basically what you need to create an instance of what's known as the general purpose allocator, which is in the standard library in the heap namespace. And the general purpose allocator, as the name suggests, is the allocator that you will probably be using the most for a general wide swath of use cases. There are many other allocators in Zig for specific strategies of allocation, but when you don't need a real specific allocation strategy and you just need to allocate memory, the general purpose allocator is the ideal allocator for that case. And what we need to do, first of all, we are declaring this variable GPA, and this general purpose allocator here is a generic function. It's basically generating the type for the general purpose allocator. It takes a configuration struct, which here we're just passing in an empty literal here. So we're using just the defaults. And this will return a type. And these other curly braces here at the end are then creating an instance of the type. Okay? And the next thing that we're going to be doing is we're going to defer a call to gpa.deinit. This deinitialization of the general purpose allocator will free any resources that are being currently used by the allocator. And it will return some diagnostic information, which in most cases you can just ignore, like I'm doing here with the underscore, or you can check out the documentation for the general purpose allocator and see the details of that information that the init returns to make good use of that information. And here we are declaring this constant allocator, which is the result of calling the allocator method on that instance of the GPA. And what this does is it returns the actual allocator implementation, because allocator in Zig is an interface. What we're first going to be looking at is when you need to allocate memory on the heap for one object, you're going to be using the create method of the allocator interface. So for example, let's say here const ptr for pointer, and we're going to try, because allocation can fail, you can run out of memory, and in that case the allocator methods would return an out of memory error. And we say here allocator.create, and you just give it the type. In this case, let's say it's a U8. So we are allocating here just 1 byte of memory. With the create method, this will return a pointer to that byte. And now we can do pointer.star to the reference and assign something. Okay, so here we're assigning the value 42 to that allocated byte in the heap. And now let's print here. Let's use here the star format specifier to print out PTR. Okay? And we save this, and let's move over here to this window. So let's do a Zig build run here. And as you can see, we do have the output here of that print using the star format specifier. Tells you it's a U8 and it gives you the memory address. But we also have this error report here that says that memory address, and it's specifically that same address that we're looking at right here is leaked. Okay, and then it'll tell you here, it's saying that here in this line, when we do this create, this is where we are leaking memory. We are allocating this memory, but we are not freeing it anywhere. And this happens because the general purpose allocator, when you're in debug mode or in release safe mode, we can try that. Say build run -d. Okay, release safe. And as you can see here, we have also the error report isn't as extensive, but it still detects and notifies us of a memory leak. Okay, so let's go back here, and what we can do is at the end of our program, for example, we can do an allocator.destroy ptr. Okay, destroy is the counterpart to create. Okay, when you create a single item, when you allocate it on the heap, then you have to use destroy with the pointer that you received from create. So let's save this, and let's move over here. Let's clear the screen, and let's do a sig build run, and there we go. We no longer have the memory leak. Now we go back here. Let's look at an example of something that can happen. Let's call this function fail. Let's say that it returns an error or void, and this is always going to fail, returning the error fail. Okay, and now if we call this try fail here, whoops, fail, and let's build and run this once again, we're going to see, let's scroll up here, that we have our output once again, and once again we have our memory leak, and down here we have the fact that we had an error during the execution, and it points to exactly in that function where we return error.fail, and here when we're doing the try on that function call. So what's going on here is, let's go back here, that we are at the end of main. We are trying to free that memory that we allocated, but we have an error before that's happening. So this try here is going to return the error that fail is returning, and we are never calling this destroy method. So we can deal with this by, let's take this out of here, and immediately after we allocate, what we're going to do, defer allocator.destroy pointer. Okay, and now let's go back here, let's sig build run, and now we get our error report as we did before, but we no longer have the memory leak. So defer is handling the case where we have an error condition, and in that case we are going to call the destroy. But now if we remove, let's comment this out, and we no longer have that error condition, then we have our memory leak once again. Okay, so the way that we deal with that is that if we need to unconditionally, no matter if it's an error or a success situation, we're going to be using defer. Okay, and in this case now, let's save this, let's run it. We no longer have the memory leak. Let's uncomment this, and let's run this again. And now, even though we have our error, as it's being reported here, we don't have the memory leak. So the defer is handling the circumstance of freeing this pointer no matter what. Okay, so that's the difference between defer and defer, and it's really important when we're doing memory allocation. And the convention, what's recommended is that we're going to have immediately after you do the allocation, you're going to have that defer to handle the cleanup of those resources. And this is how in Zig we can really reduce memory leaks compared to how you do it in C. Now let's once again comment this out, and let's see an example. A const slice equals try allocator dot, and this time we're going to use alloc. Okay, and alloc is when you need to allocate more than one item. Let's once again, we're going to be allocating bytes, and let's say that we're going to allocate 2 bytes. Okay, and let's do our defer allocator. And instead of destroy, when it's more than one item and you're getting back a slice from that allocator.alloc, instead of destroy, we're going to be using free. So here we pass that slice that we received. And now let's copy this. And here, instead of the pointer, let's do the D format specifier. And here, let's substitute this for slice. Okay, and there you go. The slice is created, but as you can see, we just have garbage data. Okay, now we don't want that garbage data. We can do slice 0 equals 42, and slice 1 equals 43. Let's save this. Let's move over to this window. And now we have 42 and 43. Okay? So basically, here we see these are the 2 primary methods that you're going to be using when dealing with allocators. You're going to be using create with its counterpart destroy when you're dealing with just one item. And this item, right now we're just allocating a byte, but this can be any type, okay? So you can have your own arbitrary custom struct type of arbitrary complexity, and you can create or allocate that struct on the heap by using create, and then free that space with destroy. And if you need more of them, then you use alloc, and you free them with free, okay? Now I wanted to demonstrate, we're going to be needing here, let's use const mem stud mem, and let's use const unicode equals stud unicode. Okay, we're going to be doing some unicode processing here, and let's say that go over here to the bottom of main, and I have a slice here. This is a string. Let's do this the other way around. Okay, I have here an array of code points. Okay, code points in Zig, you can create them by using the literal syntax here with the single quote. And the type is going to be a U21, okay? And here we have this array of code points. We have the H, we have the E with the accent, we have LLO, we have space, and we have our friendly little Ziguana here. And what we're going to be doing is we're going to create a function that takes this type of slice of code points, and we want to encode it into a slice of bytes encoded as UTF-8. So let's start that out. Let's say function as bytes, okay? And what we need here is our code points. It's going to be a slice of const U21. And here we're going to be returning a slice of U8, okay, which is a slice of bytes. But within this function, we're going to be encoding each code point to the actual bytes in UTF-8 encoding. And the thing with UTF-8 is that it's a variable size encoding, so a code point can take anywhere from 1 to 4 bytes. So we have no way of knowing ahead of time what the size of the resulting slice of bytes is going to be. And when we have that type of situation is precisely one of the primary use cases for an allocator. If we knew the size that we needed ahead of time when we're going to be compiling at compile time, then we can just use an array. We can create an array because the size of the array has to be known at compile time. So you can create an array, and then you can use that array to store your data. But if you don't know at compile time how much size you're going to need, how much space you're going to need, then you're going to need an allocator. So that's what we're going to be doing here. Let's be taking here an allocator, which is going to be of type mem allocator. And as you can see here, this is the convention in Zig. When you're going to have a function that needs to allocate on the heap, you take in an allocator as the very first parameter, okay? And what we're going to be doing here, we're going to be making use of a data structure that comes in really handy for these types of situations, which is the array list. Let's create here a list, a stud array list of bytes. And let's initialize it with our allocator, the allocator that's being passed in. And here, let's do a defer list.deinit. Okay? And we're going to be needing a way to look at, or basically to encode these code points. So let's create here a buffer. Buff. It's going to be 4 bytes. Let's say undefined here. And why 4 bytes? Because we know that each code point, when encoded, it's going to be from 1 to 4 bytes. It can't be greater than that. So we can use an array for this. And what we're going to be doing is, let's do a for loop here for code points to iterate over our slice of code points. And then in the body of this loop, let's say const len equals try Unicode UTF-8 encode. And what encode asks for is the code point and a slice for it to write the bytes. So we pass in, we take the address of the buffer, which will be coerced to a slice. Okay, and then we are that returns how many bytes were actually encoded. So now we can do a try list.append slice, and the actual slice, which is going to be buff from 0 to len. Okay, and at the end of this function we can return try list.toOwnSlice. This method from array list to own slice, it will empty out the array list and return the actual slice of items which are allocated on the heap, and that's exactly what we want. So here in our return type, we need also to add here that this can return an error. Because we are allocating here when we do, first of all, it can be an error encoding here. That's why we have this try here. And it can be an error when we are appending to the list, which would be an allocation, memory allocation error. Okay, so we have those 2 types of errors that could happen. And then we return this. Since we are basically detaching that allocated memory from the list, then this list.dinit that's going to happen at the end of this function, it's going to liberate all the resources used by the array list, but the items aren't going to be touched because they have been detached from the list by this call to onSlice. Okay, so now here we have our code points, and what we're going to be doing, let's say const stir out equals try as bytes, and whoops, that's not it, as bytes, our allocator, and our quote points in. Okay, and now this is returning a slice of bytes which we have to free. So let's do a defer allocator dot free stir out, and now let's do a for stir out byte, and let's do a print of that byte. Let's print it out as hexadecimal with a space. Okay, and then finally let's add here a new line for some spacing. Whoops. Oh yeah, I had this so the compiler would not complain that we weren't using code points in, so we can remove that. And now we don't have any errors. Let's move over here and let's sig build run. And yes, of course, we're going to have some errors. What do we have here? It says that, oh yeah, code points in is an array. It's not a slice. So what we got to do here is we got to take the address, and that will be coerced to a slice. Let's try that again, and here we go. So we have the result of these bytes, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 bytes. Let's go back here. We have 1, 2, 3, 4, 5, 6, 7 code points, which turned into 11 bytes. So that's precisely what I was saying. We have this situation that given that UTF-8 is a variable size encoding, we're not going to know ahead of time how many bytes we need. So in this case, our allocator provides that flexibility. In this case, we are going from 7 code points to 11 bytes. Okay. Now, what happens if we want to go in the other direction? We want to convert from a slice of bytes to code points. So let's see an example of doing that. Let's see, create another function here. Function as code points alloc. And let's take here once again an allocator, which is going to be a mem.allocator, and we are going to take the stir, which is a slice of const U8, and we're going to be returning a slice of U21. Okay, so we're going to be doing the same thing. Let's create here a list, a stud array list. Whoops, that's not it. Array list of U21. Let's initialize it with our allocator. Let's defer here list.dinit. And we're going to be needing a view into our string as UTF-8, and the Unicode namespace provides for that. Let's create var view here, try unicode.utf8 view, init, and we give it here the stir. And once we have the view, we can create an iterator. View.iterator. And what we're going to be doing is, while iter.next, next code point, cp. We're going to try append cp, and this time it's not append slice, it's just append, because we're just appending one item at a time. And actually, since this is just a one-liner, we can just put it right here, and then at the end we do a try, return try list.to own slice. Okay, so now we go down here. We're going to const points out. I'm going to try as quote points alloc, allocator, and let's pass in our stir out. Okay, and now we have to remember to free allocator.free code points out, and let's just copy this, paste it here, code points out cp, and let's print this as a Unicode value cp here, and then we have a new line, and I think let's do it in the other window. See build run, and yeah, exactly, there we go. Here we have the actual code point. So we went back from our bytes that we encoded as UTF-8 back to our code points, which are the 7 code points that we had in the beginning. But in this situation, I want to show you that in contrast to the initial conversion from code points to bytes, technically, when we're going from bytes to code points, we do have a maximum amount of space that we know this process cannot exceed. Each code point can be from 1 to 4 bytes. So the final result of converting bytes to code points cannot be larger than the size of the bytes themselves. Okay, so the input string, the size of that in bytes is a maximum. The amount of code points cannot exceed that. So we can create, let's create here, let's copy this, okay, and we can create a version which is not alloc, and let's delete this. We take the string, and here we're going to take a slice of U21, okay, and basically this is a technique that's used a lot in the world of C. We have basically what's known as an outvar, a variable that we're going to be using to put our data in instead of having to allocate. And then we're going to return a slice. So this slice is going to be a slice that we're going to create from this input slice that we have here. So the output is actually going to be a slice of this argument that's going to be passed in. And now we don't need to allocate here a list. And we have our view, and what we're going to be doing, let's create here var I is view size equals 0. And now we're going to be needing here a body, because it's not going to be just a one-liner. And what we're going to be doing is we're going to be saying that out I equals CP, and then I plus equals 1. And you know what? We can do this as part of the while syntax. We can do this, I plus equals 1. Remove this from here, and now it can be once again a one-liner. And here we no longer have to do this. What we're going to be doing is out from 0 to I. Okay? So we're basically copying the code points one by one into this output slice. And then we are returning a slice going from 0 to the total, which is going to be the value of I once we finish this loop. Okay? So let's copy all of this. Let's make some space here and paste it here. We're going to be needing a couple of things now. Let's see, I have this version here. It's called stir in, and stir in has the bytes once again of our code points as bytes. And we also are going to need, let's make a buffer here, which is going to be stir in.len of u21, which equals undefined. Since we're going to be creating this buffer, which is an array, and the size of the array has to be known at compile time, this is why I'm going to be using this string literal, because this is known at compile time. The size of this string literal is going to be known at compile time, and that's what I'm going to be using here, the length field of that string as the size of this u21 array. As I said, you can't have more code points than bytes in the original string. So this is a maximum here. Now, let's make this code points 2. We're not going to be using the alloc version, so we can delete this. And here we can use our buffer now. We don't have to free this. And let's add here 2. And I think with that, we are basically done. Okay, we have this new version that's not allocating. We're basically allocating on the stack using this array. So let's move over here and let's run this. And there you go. As you can see, once again, we have the exact same code points as we had before. So that version is also working, and we don't have any memory leaks or anything like that. So here you see this is a typical situation when you're having to make decisions in Zig of whether you need to use an allocator or not. If you know the size or a maximum possible size that you need ahead of time at compile time, then you probably can get away with just allocating on the stack, as we're doing here, this array, and then creating a function that takes that a slice of that and will write the data to that slice, okay, as we're doing here. And as you can see, we don't need to free any resources because we aren't using an allocator. But if you don't know ahead of time, as is the case in our first example, when we're going from code points to bytes, you really can't know ahead of time, then that's a classic situation where you're going to need an allocator. And here you have an example of that situation. So I hope you find this useful. Dude the Builder here. I'll see you in the next one.